for thousands of years, when darkness settled across the Australian outback and the sky transformed into a river of light, Aboriginal elders would point toward the darkest patches within that glowing band and speak of the great celestial emu, its body formed not from stars but from the spaces between them, its head resting near the Southern Cross, and its long neck stretching toward the very heart of what we now call the Milky Way, where the sky burns brightest and most mysterious. Ancient eyes on the galactic heart. Long before telescopes existed, long before humanity understood that we lived within a vast spiral galaxy, people across every continent gazed upward at that luminous river crossing the night sky and created stories to explain its beauty. The galactic centre, that region where the Milky Way appears widest and brightest, held particular fascination for ancient observers. Though they could not have known they were looking toward a supermassive black hole surrounded by billions of stars, they sensed something profound resided there, something worthy of myth and reverence. The Aboriginal Australians developed one of the oldest continuous astronomical traditions on Earth, stretching back perhaps 60,000 years. Their observations of the galactic centre region gave rise to the celestial emu, a constellation defined not by connecting bright stars, but by tracing the dark nebulae that wind through the Milky Way. The emu's head appears near the Coalsack Nebula beside the Southern Cross, and its body extends along the galactic plane towards Scorpius and Sagittarius, precisely where the galactic centre resides. When the emu appeared in certain orientations, it signalled the time for gathering emu eggs, demonstrating how intimately these ancient astronomers understood the sky's seasonal patterns. The dark dust lanes they incorporated into their constellation are the very same clouds of gas and debris that obscure our view of the galactic centre today, blocking visible light from reaching our eyes. Across the Pacific, the Inca civilization of South America developed remarkably similar traditions. They too recognized the dark clouds within the Milky Way as meaningful shapes, calling them dark cloud constellations or Yanafuyu. The Incas identified a llama and her calf, a fox, a toad, a serpent, and a partridge within these shadowy regions. Their astronomical knowledge was sophisticated enough that they built structures aligned to celestial events, and the Milky Way itself, which they called Mayu, or the Celestial River, held central importance in their cosmology. The river flowed from the heavens through the underworld and back again, and its brightest region represented a place of cosmic significance where the waters gathered most densely. The Mesoamerican civilizations, including the Maya, developed extraordinarily precise astronomical systems. The Maya observed the Milky Way with careful attention, noting how it appeared to rotate through the night, sometimes standing upright like a great tree connecting earth and sky, other times lying horizontal across the heavens. They associated the dark rift near the galactic centre with Xibalba, the underworld, and the bright band itself with the world tree or the white road walked by souls after death. The galactic centre region, where the Milky Way achieves its greatest brilliance, marked a cosmic crossroads of profound spiritual importance. Maya astronomers tracked the movements of planets against this backdrop with accuracy that still impresses modern scientists, recording their observations in codices and carved monuments. In the Mediterranean world, the ancient Greeks gave us the very name we still use today. The word galaxy derives from the Greek galaxias, meaning milky, which itself comes from gala, the word for milk. Greek mythology explained the Milky Way as milk sprayed across the sky when the infant Heracles suckled too vigorously at the breast of the goddess Hera. Other Greek thinkers moved beyond mythology to propose naturalistic explanations. The philosopher Democritus, who lived around 400 years before the Common Era, suggested that the Milky Way consisted of countless distant stars, too faint to distinguish individually. This remarkable insight, though impossible to verify at the time, proved essentially correct more than 2,000 years later when Galileo turned his telescope skyward. The Roman poet Ovid wrote of the Milky Way as the palace road of the gods, a celestial highway leading to the dwelling of Jupiter. Roman astronomers adopted Greek astronomical knowledge and terminology, passing it eventually to medieval European scholars. The brightness of the galactic centre region, visible from Mediterranean latitudes during summer months, would have appeared as the most magnificent portion of this divine roadway, though it never rises as high in northern skies as it does for observers closer to the equator. Chinese astronomical traditions developed independently and with extraordinary sophistication. Chinese astronomers maintained continuous records of celestial events spanning thousands of years, documenting supernovae, comets, and planetary movements with careful precision. They called the Milky Way the Silver River, or Tianhe, and it features prominently in one of China's most beloved folk tales, the story of the cowherd and the weaver girl. These two lovers, represented by the stars Altair and Vega, were separated by the Silver River and permitted to meet only once each year when magpies formed a bridge across the celestial waters. The galactic centre lies along this Silver River, part of the vast cosmic waterway that separated the star-crossed lovers. Ancient Indian astronomers knew the Milky Way as Akash Ganga, the Ganges of the sky, connecting the sacred earthly river to its celestial counterpart. The brightness of the galactic centre represented where these heavenly waters flowed most abundantly. Indian astronomical texts, some dating back thousands of years, demonstrate sophisticated understanding of celestial mechanics, and the Milky Way held important place in both scientific and spiritual traditions. The concept of vast cosmic cycles, of creation and destruction spanning enormous timescales, appears throughout Indian philosophy, presaging in some ways our modern understanding of galactic evolution. African astronomical traditions, though less documented by outside scholars, reveal deep knowledge of the night sky. The Khoisan people of southern Africa, whose ancestors may have been among the first modern humans, developed rich star lore, including stories about the Milky Way. Various African cultures associated the bright band with paths walked by ancestors, rivers of light, or the scattered ashes of campfires. The San people told of a girl who threw ashes into the sky to create the Milky Way so that people might see the stars and find their way home at night. The galactic centre, brightest portion of this ash road, would have served as a beacon in these traditions. What unites all these ancient traditions is a recognition that something special resided in that brightest region of the Milky Way. Without understanding the physics of what they observed, without knowing about black holes or stellar populations or radio emissions, people across every culture sensed that the galactic centre represented a place of cosmic importance. The concentration of light, the complex structure visible to keen eyes on dark nights, the way it dominated the summer sky from southern latitudes, all these factors contributed to its prominence in human mythology and early astronomy. The transition from mythological to scientific understanding began gradually. Medieval Islamic astronomers preserved and extended Greek astronomical knowledge, making careful observations and developing mathematical tools that would later enable European scientists to revolutionize our understanding of the cosmos. The Persian astronomer Abd al-Rahman al-Sufi produced detailed star catalogues in the 10th century that included observations of the Milky Way and what he called the Little Cloud, likely the Andromeda Galaxy, recognizing it as something distinct from ordinary stars. When Galileo Galilei pointed his improved telescope at the Milky Way in 1610, he confirmed what Democritus had suggested 2 millennia earlier. The luminous band resolved into countless individual stars, far too numerous to count, packed so densely that their combined light created the glowing river visible to unaided eyes. This discovery marked the beginning of our scientific understanding of the galaxy, though the true nature and structure of the Milky Way would remain mysterious for centuries more. The galactic centre, still hidden behind its veil of dust, would keep its secrets longest of all. The question of whether the Sun occupied a central or peripheral position in the Milky Way remained contentious into the 20th century. William Herschel, the great 18th century astronomer who discovered Uranus, attempted to map the galaxy by counting stars in different directions. His method was clever but flawed by the obscuring dust he could not detect, leading him to conclude incorrectly that the Sun resided near the centre of a relatively small stellar system. This geocentric bias placing humanity near the cosmic centre proved difficult to overcome. The breakthrough came in 1918 when Harlow Shapley studied globular clusters, those ancient spherical collections of hundreds of thousands of stars that orbit the galaxy. By measuring the distances to these clusters using variable stars as standard candles, Shapley determined that they formed a spherical halo centered not on the Sun, but on a point in the direction of Sagittarius, roughly 25,000 light-years away. The Sun, Shapley demonstrated, occupied a position far from the galactic centre out in the stellar suburbs. This discovery displaced humanity from cosmic centrality, just as Copernicus had displaced Earth from the centre of the solar system centuries before. Yet even Shapley could not see the galactic centre directly. The same dust clouds that Aboriginal Australians had incorporated into their celestial emu, the same dark rifts the Maya associated with the underworld, blocked visible light from the galactic centre as effectively as a curtain drawn across a window. To peer through that curtain would require entirely new ways of seeing. Technologies that would not emerge until the 20th century brought radio astronomy, infrared detectors, and eventually space telescopes capable of observing in wavelengths that dust cannot block. The ancient observers were right to sense something profound in that direction. What they perceived as the brightest part of a celestial river, or road, or streak of divine milk, was indeed special, a region harbouring not only dense concentrations of stars, but phenomena beyond anything they could have imagined. A supermassive black hole 4 million times the mass of our Sun, stars orbiting at thousands of kilometres per second, clouds of gas heated to millions of degrees, magnetic fields of enormous strength, and the archaeological record of our galaxy's violent and dynamic history. Their myths, in a sense, were appropriate responses to something genuinely extraordinary, stories attempting to capture significance that science would eventually articulate in different terms. As we begin our journey toward the galactic centre, we carry with us this inheritance of human wonder. Every culture that looked up and marvelled at the Milky Way contributed to the long tradition of seeking to understand our cosmic home. The Aboriginal elder pointing out the Imu, the Maya astronomer tracking planets against the galactic backdrop, the Greek philosopher proposing that the glow consisted of distant stars, all participated in the same fundamental project of making sense of the universe. Modern science continues this project with new tools and methods, but the essential impulse remains unchanged. We look up, we wonder, and we seek to understand. The birth of radio astronomy and first glimpses. The year 1932 brought an accidental discovery that would eventually open a new window onto the galactic centre. Carl Jansky, a young physicist working for Bell Telephone Laboratories in New Jersey, had been assigned to investigate sources of static that interfered with transatlantic radio communications. He constructed an antenna array mounted on a rotating platform, a contraption that earned the nickname Jansky's merry-go-round, and began systematically cataloguing the sources of radio noise. Jansky identified 3 types of interference: nearby thunderstorms, distant thunderstorms, and a mysterious steady hiss of unknown origin. The third source proved most intriguing. Over months of careful observation, Jansky noticed that this static rose and fell on a cycle of approximately 23 hours and 56 minutes, not the 24-hour cycle of solar interference. This period matched the sidereal day, the time Earth takes to rotate once relative to the distant stars rather than the Sun. The radio noise, Jansky realized, must originate from beyond the solar system. By tracking the signal's position across the sky, Jansky determined that the radio emission came from the direction of Sagittarius, precisely where Shapley had located the galactic center. In 1933, Jansky published his findings, announcing that he had detected radio waves emanating from the Milky Way itself. The discovery made front-page news in the New York Times, which declared that Jansky had heard the sound of the universe. He had, in fact, detected radio emission from the galactic center region, the first human to perceive this distant realm through any means other than visible light. Bell Labs, focused on practical communications problems, saw no commercial application for Jansky's cosmic static and reassigned him to other projects. The birth of radio astronomy might have been delayed by years had it not been for Grota Reber, an amateur radio enthusiast in Wheaton, Illinois. Fascinated by Jansky's discovery, Reber decided to build his own radio telescope in his backyard. Working alone and financing the project himself, he constructed a parabolic dish antenna, 9 meters in diameter, the first purpose-built radio telescope in history. Reber began observations in 1937 and spent years mapping the radio sky. His results, published in the early 1940s, confirmed and extended Jansky's findings. The radio emission from the direction of Sagittarius was indeed the strongest in the sky, and Reber's maps revealed a complex structure of radio sources concentrated along the galactic plane. He had created the first radio maps of our galaxy, primitive by later standards, but revolutionary for their time. The galactic center, invisible to optical telescopes, was revealing itself through radio waves. The significance of these discoveries became clearer after World War II, when radar technology developed during the conflict was adapted for astronomical purposes. Scientists who had worked on radar systems turned their expertise to building more sensitive radio telescopes, and the field of radio astronomy expanded rapidly. In 1951, Australian astronomers Jack Piddington and Harry Minnitt used a radio telescope to study the galactic center region in detail, identifying a compact source of intense radio emission. This source, located at the heart of the Milky Way, would eventually receive the designation Sagittarius A. The name Sagittarius A reflects the convention of naming radio sources by their constellation and order of discovery. The source was the first major radio emitter identified in Sagittarius, hence the letter A. Later observations revealed that Sagittarius A was itself complex, consisting of multiple components. The extended emission from hot gas and supernova remnants became known as Sagittarius A East and Sagittarius A West, while the compact central source received the designation Sagittarius AI, pronounced Sagittarius A star. The asterisk notation, borrowed from atomic physics, where it denotes an excited state, was chosen by Robert Brown in 1982 to indicate that this source was something special, something excited or extraordinary. The challenge facing early radio astronomers was understanding what physical processes could produce such intense radio emission. The galactic center region emits radio waves through several mechanisms. Hot ionized gas produces thermal radiation as electrons interact with ions. More dramatically, electrons spiraling through magnetic fields at nearly the speed of light generate synchrotron radiation, a non-thermal process that produces the intense emission characteristic of many cosmic radio sources. The presence of strong synchrotron radiation from the galactic center hinted at violent processes and powerful magnetic fields, phenomena quite different from the steady stellar light that optical astronomers studied. Radio interferometry, developed through the 1950s and 60s, allowed astronomers to achieve much finer resolution than single dishes could provide. By combining signals from multiple radio telescopes separated by large distances, astronomers could synthesize the resolving power of an antenna as large as the separation between the individual dishes. This technique, called aperture synthesis, earned Martin Ryle the Nobel Prize in Physics and opened new possibilities for studying compact radio sources like Sagittarius A. Through the 1960s and 70s, increasingly sophisticated radio observations revealed the galactic center as a region of extraordinary activity. Astronomers detected complex molecules in the dense gas clouds surrounding the center, discovered supernova remnants and regions of active star formation, and measured the motions of gas clouds orbiting the central source. The picture emerging was of a dynamic, energetic environment, quite unlike the quiet stellar neighborhoods surrounding our Sun. The compact nature of Sagittarius A became increasingly apparent. Very long baseline interferometry, which links radio telescopes on different continents to achieve extremely high resolution, showed that the central radio source was remarkably small. By the 1980s, observations had constrained Sagittarius A to a region smaller than our solar system, yet it somehow dominated the gravitational dynamics of stars and gas for light years around. The combination of small size and large gravitational influence pointed toward an extraordinary concentration of mass, though the nature of that concentration remained debated. Radio astronomy had achieved what visible light could not. It had pierced the dusty veil hiding the galactic center and revealed a realm of intense activity centered on a compact, powerful source. Yet radio waves alone could not tell the complete story. The galactic center emits radiation across the entire electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, X-rays, and gamma rays. Each wavelength range reveals different physical processes and different components of this complex region. The full picture would require observations spanning all these wavelengths, a multispectral approach that would develop over the following decades. The journey from Jansky's accidental detection of cosmic static to our current understanding of Sagittarius A spans nearly a century of technological development and scientific insight. Each generation of radio telescopes has revealed new details, new mysteries, and new questions about the heart of our galaxy. The static that once interfered with telephone calls turned out to be a message from the cosmos, an invitation to explore a realm that human eyes could never see, but human ingenuity could learn to perceive. Understanding our galaxy's architecture, to appreciate what lies at the center of the Milky Way, we must first understand the grand structure of the galaxy itself. Our cosmic home is a barred spiral galaxy, a vast rotating system of stars, gas, dust, and dark matter spanning approximately 100,000 light-years from edge to edge. The Sun and its planets occupy a position roughly 26,000 light-years from the center, embedded within one of the spiral arms that give our galaxy its characteristic shape. Imagine looking down upon the Milky Way from a great distance above the galactic plane. You would see a bright central region surrounded by a flattened disk from which spiral arms extend outward like the arms of a pinwheel. A bar-shaped structure of stars passes through the centre, connecting opposite sides of the inner galaxy. This bar, whose existence was confirmed only in recent decades through infrared observations, distinguishes the Milky Way as a barred spiral rather than a simple spiral galaxy. The bar plays an important role in the dynamics of the inner galaxy, channeling gas toward the centre and influencing the orbits of billions of stars. The spiral arms are not solid structures but rather density waves, regions where stars and gas are temporarily compressed as they orbit the galactic centre. Stars pass through the arms much as cars pass through a traffic jam, slowing down in the denser regions before speeding up again as they emerge. The compression triggers star formation, which is why the spiral arms appear bright with young blue stars and glowing nebulae. Our Sun has passed through multiple spiral arms during its journeys around the galaxy, experiencing different cosmic environments over its 4.5 billion year history. The disk of the Milky Way is remarkably thin compared to its diameter. If the galaxy was scaled down to the size of a dinner plate, the disk would be thinner than a sheet of paper. This thin disk contains most of the galaxy's gas and dust, along with younger stars that formed from this material. An older population of stars occupies a thicker disk component, stars that formed earlier in galactic history when the disk was puffier and less settled. The interplay between thin and thick disk populations tells the story of how the galaxy evolved over billions of years. Surrounding the disk is the stellar halo, a roughly spherical distribution of old stars and globular clusters extending far beyond the visible disk. These ancient objects, some nearly as old as the universe itself, preserve information about the galaxy's earliest history. Many halo stars and globular clusters may have originated in smaller galaxies that the Milky Way absorbed over cosmic time, their disrupted remains now scattered through the halo. The globular clusters that Shapley studied to locate the galactic centre are members of this halo population, ancient sentinels orbiting the galaxy on elongated paths that carry them far from the disk. At the heart of everything lies the galactic bulge, a dense concentration of stars surrounding the centre. The bulge is not a simple sphere, but rather a triaxial structure, elongated along the bar that passes through it. Stars in the bulge follow complex orbits quite different from the nearly circular paths of disk stars like our Sun. Some bulge stars are very old, formed in the earliest epochs of galactic history, while others are younger, born from gas that accumulated in the central regions over time. The bulge contains perhaps 10 billion stars packed into a volume only a few thousand light-years across, creating stellar densities far higher than we experience in the solar neighbourhood. Within the bulge lies the nuclear stellar disk, a flattened structure of stars roughly 500 light-years in diameter rotating around the galactic centre. This disk represents a distinct stellar population, likely formed from gas that accumulated in the central regions over the past few billion years. The nuclear stellar disk is in turn surrounded by the central molecular zone, a vast complex of dense gas clouds that we will explore in detail shortly. The Sun's orbit around the galactic centre takes approximately 230 million years to complete, a period sometimes called a galactic year or cosmic year. Since the Sun formed 4.5 billion years ago, it has completed roughly 20 orbits around the galaxy. During this time, the Sun has experienced varying cosmic environments, passing through spiral arms, encountering different stellar populations, and possibly even experiencing close passages to other stars. The dinosaurs lived and went extinct in less than 1 galactic year, and all of recorded human history spans less than 100,000th of a single orbit. Our orbital velocity around the galactic centre is approximately 220 kilometers per second, a speed that seems enormous by everyday standards, but is typical for stars in this region of the galaxy. At this velocity, light from the galactic centre still takes 26,000 years to reach us, demonstrating the vast scales involved. When we observe the galactic centre today, we see it as it appeared 26,000 years ago, during the last ice age on Earth, when woolly mammoths roamed and our ancestors were creating cave paintings in Europe. The mass of the Milky Way is difficult to measure precisely because much of it consists of dark matter, a mysterious substance that exerts gravitational influence but neither emits nor absorbs light. Current estimates suggest a total mass of approximately 1 to 2 trillion solar masses, with dark matter comprising perhaps 80 to 90% of this total. The dark matter is distributed in a vast halo extending far beyond the visible galaxy, its presence revealed through its gravitational effects on stellar motions and the rotation of the galactic disk. The rotation curve of the Milky Way, which describes how orbital velocity varies with distance from the centre, provided some of the earliest evidence for dark matter. In a system dominated by visible matter, orbital velocities should decrease with distance from the centre, following Kepler's laws as planets do in the solar system. Instead, the Milky Way's rotation curve remains relatively flat at large distances, indicating the presence of additional mass beyond what stars and gas can account for. This dark matter halo, though invisible, shapes the dynamics of the entire galaxy. The Milky Way does not exist in isolation. It is the largest member of the local group, a collection of more than 80 galaxies bound together by gravity. The Andromeda Galaxy, slightly larger than the Milky Way, is the other major spiral in the local group, and the two galaxies are approaching each other at roughly 110 kilometers per second. In approximately 4 to 5 billion years, the Milky Way and Andromeda will collide and eventually merge, forming a larger elliptical galaxy, sometimes nicknamed Milkomeda. The galactic centers of both systems will eventually coalesce, their supermassive black holes spiraling together and merging in an event that will release enormous energy in gravitational waves. Understanding the architecture of the Milky Way provides essential context for appreciating what lies at its center. The galactic center is not merely a geometric point but a physical region shaped by the accumulation of matter over billions of years. Gas flowing inward along the bar, stars formed from compressed molecular clouds, the remnants of disrupted, smaller galaxies, all have contributed to building the dense, active environment we observe today. The supermassive black hole at the very centre is both a product of this accumulation and a driver of further evolution, its gravity shaping the orbits of nearby stars and its occasional feeding episodes releasing energy that affects the entire galaxy. The central molecular zone, a cosmic cauldron. As we approach the galactic centre, we first encounter the central molecular zone, a vast reservoir of dense gas extending roughly 1,500 light-years across the inner galaxy. This region contains an estimated 60 million solar masses of molecular gas, representing perhaps 10% of all the molecular gas in the entire Milky Way, concentrated in less than 1% of its volume. The central molecular zone is a cosmic cauldron where extreme conditions prevail, where giant molecular clouds collide and compress, where stars form in violent bursts, and where the influence of the central black hole begins to make itself felt. The gas in the central molecular zone is predominantly molecular hydrogen, the same material from which stars form throughout the galaxy. However, Conditions here differ dramatically from the quiet molecular clouds in the solar neighbourhood. Temperatures in the central molecular zone range from tens to hundreds of Kelvin, significantly warmer than typical molecular clouds elsewhere in the galaxy. The gas is denser, more turbulent, and subjected to stronger tidal forces, magnetic fields, and radiation than clouds in the galactic disk experience. One of the most remarkable features of the central molecular zone is the complex chemistry occurring within its clouds. Astronomers have detected dozens of different molecular species in this region, including complex organic molecules that represent steps along the path toward the chemistry of life. Molecules like methanol acetone and ethyl formate have been identified in the gas clouds near the galactic center. The detection of these complex molecules in such an extreme environment demonstrates that the building blocks of organic chemistry can form under a wide range of cosmic conditions. Sagittarius B2, located approximately 390 light-years from the galactic center, is one of the largest and most massive molecular clouds in the entire galaxy. This single cloud complex contains roughly 3 million solar masses of gas and is one of the most prolific sites of star formation in the Milky Way. Within Sagittarius B2, astronomers have discovered an astonishing variety of molecules, including aminoacetonitrile, a molecule related to the simplest amino acid glycine. The chemistry occurring in this cloud represents a natural laboratory for studying how complex molecules form in space. The Arches cluster, located approximately 100 light-years from the galactic center, is one of the densest known star clusters in the galaxy. This young cluster, only about 2 to 4 million years old, contains roughly 150 of the most massive and luminous stars known, packed into a region less than 2 light-years across. The stars in the Arches cluster are so massive and hot that they will exhaust their nuclear fuel quickly, exploding as supernovae within the next few million years. The cluster's existence demonstrates that extreme star formation can occur even in the hostile environment near the galactic center. Nearby lies the quintuplet cluster, another young massive star cluster, named for 5 prominent infrared sources identified in early observations. Like the Arches cluster, the quintuplet contains massive luminous stars that will soon end their lives explosively. The cluster also hosts the Pistil star, one of the most luminous stars known in the galaxy, shining with the light of millions of suns. The Pistil star is surrounded by the Pistil nebula, a shell of gas expelled by the star in violent eruptions. Stars this massive burn through their fuel at prodigious rates and live only a few million years, cosmic mayflies compared to the 10 billion year lifespan of a star like our Sun. The presence of these young massive star clusters near the galactic center poses interesting questions about star formation in extreme environments. The strong tidal forces near the center should tear apart molecular clouds before they can collapse to form stars. Yet clearly, star formation does occur. The answer may involve the collision and compression of gas clouds as they orbit the center, creating conditions dense enough to overcome the disruptive tidal forces. The bar structure of the inner galaxy may channel gas inward, feeding the central molecular zone and triggering episodes of enhanced star formation. Magnetic fields in the central molecular zone are remarkably strong, hundreds of times more powerful than the average galactic magnetic field. These fields are revealed through radio observations of polarized emission and through the alignment of dust grains within the gas clouds. The magnetic field structure is complex, with both organized large-scale components and tangled small-scale features. Near the galactic center itself, the magnetic field becomes even stronger, reaching milligauss levels that influence the behavior of charged particles and the dynamics of the gas. One of the most striking features of the galactic center region is the presence of hot plasma, with temperatures reaching millions of degrees. This extremely hot gas, detected through its X-ray emission, fills much of the central region and extends outward in structures that may connect to the Fermi bubbles we will discuss later. The origin of this hot plasma remains somewhat uncertain, but likely involves energy injection from supernova, stellar winds from massive stars, and possibly outbursts from the central black hole. The plasma is too hot to be gravitationally bound to the galaxy and must be continuously replenished by ongoing energetic processes. The central molecular zone is threaded by mysterious filamentary structures, visible in radio observations. These non-thermal radiofilaments, discovered in the 1980s, extend for tens of light years perpendicular to the galactic plane. They appear to trace magnetic field lines and emit synchrotron radiation from electrons spiraling along the fields at nearly the speed of light. The origin of these filaments and the source of the energetic electrons they contain remain active areas of research. They may be related to past activity from the central black hole or to energetic processes within the central molecular zone itself. The gas dynamics in the central molecular zone are complex and violent. Clouds orbit the galactic center on eccentric paths, sometimes colliding with each other at velocities of tens of kilometers per second. These collisions compress the gas, potentially triggering star formation, and create shock waves that heat the surrounding medium. The orbital motions are influenced by the bar potential of the inner galaxy, which creates resonances and drives gas inward toward the center. Some gas may eventually fall all the way to the central black hole, providing fuel for occasional accretion episodes. A particularly intriguing structure is the circumnuclear disk, a ring of dense molecular gas orbiting the galactic center at a distance of roughly 5 to 10 light years. This disk, containing perhaps 10,000 solar masses of gas, represents the innermost reservoir of molecular material, the last staging area before gas potentially falls toward the black hole. The circumnuclear disk is clumpy and asymmetric, with dense knots and streamers of gas that may represent material being tidally disrupted as it approaches the center. The central molecular zone is not a static structure, but rather a dynamic system constantly processing gas through star formation, stellar evolution, and accretion toward the center. Gas flows in from the larger galaxy, accumulates in the central molecular zone, forms stars, and is partially returned to the interstellar medium through stellar winds and supernovae. Some fraction continues inward toward the black hole, while energy released by all these processes drives gas outward in fountains and outflows. The central molecular zone represents a kind of cosmic ecosystem, with energy and matter cycling through various phases in a complex dance choreographed by gravity, magnetic fields, and radiation. Sagittarius A, the supermassive black hole. At the very heart of the Milky Way, at the precise centre of all this swirling activity, lies Sagittarius A, a supermassive black hole containing approximately 4 million times the mass of our Sun. This extraordinary object, compressed into a region smaller than the orbit of Mercury, represents the gravitational anchor of our entire galaxy. Every star in the Milky Way, including our Sun, orbits around this central mass, bound by its gravity across distances spanning tens of thousands of light years. The concept of a black hole, an object so massive and compact that nothing can escape its gravitational pull, not even light, emerged from Einstein's general theory of relativity in the early 20th century. Carl Schwarzschild calculated the first black hole solution to Einstein's equations in 1916, just months after general relativity was published. The Schwarzschild radius, the size of the event horizon for a non-rotating black hole, depends only on the mass of the object. For a black hole of 4 million solar masses, like Sagittarius A, the Schwarzschild radius is approximately 12 million kilometers, or about 17 times the radius of the Sun. The event horizon of Sagittarius A is not a physical surface, but rather a mathematical boundary beyond which events cannot influence the outside universe. Anything crossing the event horizon, whether matter, light, or information, is forever lost to outside observers. The interior of a black hole, according to general relativity, contains a singularity where density becomes infinite, and our current physical theories break down. What actually happens at the singularity remains one of the great unsolved problems in physics, likely requiring a quantum theory of gravity to resolve. Despite its enormous mass, Sagittarius A is remarkably compact. The event horizon would fit comfortably within the orbit of Mercury around our Sun. Yet this compact object dominates the dynamics of the entire central region of the galaxy. Stars within a few light years of the centre orbit Sagittarius A at tremendous velocities, their paths determined by the black hole's gravitational field. Gas clouds and stellar debris that venture too close are torn apart by tidal forces and may eventually be consumed by the black hole. The mass of Sagittarius A has been measured with extraordinary precision through observations of stars orbiting close to the black hole. By tracking the positions and velocities of these stars over years and decades, astronomers can apply Kepler's laws to determine the mass of the central object. The most precisely measured orbit belongs to a star called S2, which completes one orbit around Sagittarius A every 16 years. The orbital parameters of S2 and other nearby stars consistently indicate a central mass of approximately 4 million solar masses, concentrated within a volume small enough that only a black hole can explain the observations. One of the most surprising aspects of Sagittarius A is how quiet it is. Supermassive black holes in other galaxies often power active galactic nuclei, brilliant sources of radiation that can outshine all the stars in their host galaxies combined. These active black holes are surrounded by accretion disks of infalling material heated to millions of degrees, producing intense emission across the electromagnetic spectrum. Quasars, the most luminous active galactic nuclei, are visible across billions of light years and represent the most energetic, sustained phenomena in the universe. By contrast, Sagittarius A is remarkably dim. Its luminosity is roughly 100 million times less than would be expected if it were accreting material at the maximum possible rate. The black hole at the centre of our galaxy is essentially starving, consuming only a tiny trickle of material compared to its potential appetite. The accretion rate onto Sagittarius A is estimated at roughly 100,000th of a solar mass per year, a pittance compared to the voracious feeding of active galactic nuclei. Why is Sagittarius A so quiet? The answer likely involves the properties of the gas in its vicinity. The hot, tenuous plasma surrounding the black hole does not cool efficiently and therefore does not settle into a thin, dense accretion disk. Instead, the gas forms a thick, puffy structure that accretes inefficiently. Much of the energy released by infalling material may be advected into the black hole rather than radiated away, further reducing the observable luminosity. The feeding habits of Sagittarius A can be compared to a gentle stream rather than a raging river. Material drifts toward the black hole slowly, hesitantly, as if uncertain whether to take the final plunge. The hot gas surrounding the event horizon swirls in complex patterns, some of it falling inward, while other portions are flung outward by magnetic forces and radiation pressure. This inefficient accretion process means that Sagittarius A releases only a tiny fraction of the energy it could potentially produce, making our galactic centre a remarkably peaceful place compared to the violent hearts of active galaxies. The environment immediately surrounding Sagittarius A is nonetheless extreme by any earthly standard. Within a few hundred Schwarzschild radii of the event horizon, temperatures reach billions of degrees, and magnetic fields achieve strengths millions of times greater than Earth's magnetic field. Electrons spiral along magnetic field lines at nearly the speed of light, producing the radio emission that first revealed Sagittarius A to human observers. This radio emission, though faint compared to active galactic nuclei, remains the primary way we detect and study the immediate vicinity of the black hole. Sagittarius A does not remain perfectly constant in its emission. Observations reveal variability on timescales ranging from minutes to hours, with occasional flares that briefly increase the luminosity by factors of 10 or more. These flares occur in radio, infrared, and X-ray wavelengths, suggesting that energetic events periodically disturb the flow of material near the black hole. The cause of these flares remains debated, but possibilities include magnetic reconnection events, where tangled magnetic field lines suddenly snap and release energy, or the tidal disruption of small objects, like asteroids, that venture too close to the black hole. The X-ray emission from Sagittarius A is particularly interesting. In its quiescent state, the black hole produces only feeble X-rays, barely detectable even with sensitive space telescopes. However, X-ray flares occur roughly once per day on average, briefly increasing the X-ray luminosity by factors of up to 100. These flares typically last for an hour or so before fading back to the quiescent level. The frequency and intensity of X-ray flares provide clues about the accretion process and the magnetic field structure near the event horizon. One of the most intriguing aspects of Sagittarius A is the evidence that it was much more active in the relatively recent past. X-ray observations of molecular clouds in the galactic center region reveal fluorescent emission that appears to be the echo of a powerful X-ray flare from Sagittarius A that occurred a few hundred years ago. The X-rays from this flare travelled outward and illuminated the molecular clouds like a cosmic flashlight, and we now see the reflected glow reaching us from different clouds at different times as the light echo propagates through the region. The intensity of this historical flare was roughly 1,000,000 times greater than the current luminosity of Sagittarius A, suggesting that the black hole experienced a significant feeding event within the past few centuries. Perhaps a gas cloud or an unfortunate star ventured too close and was partially consumed, temporarily awakening the sleeping giant at our galaxy's heart. Such events may occur sporadically throughout the black hole's history, punctuating long periods of quiescence with brief episodes of enhanced activity. The mass of Sagittarius A, 4 million solar masses, places it in the category of supermassive black holes, though it is actually on the smaller end of this class. Supermassive black holes in other galaxies range from about 1 million to tens of billions of solar masses, with the largest known examples exceeding 40 billion solar masses. These titans reside at the centres of giant elliptical galaxies and likely grew through the merger of smaller black holes and the accretion of vast quantities of gas over cosmic time. The relationship between supermassive black holes and their host galaxies represents one of the most important discoveries in extragalactic astronomy over the past few decades. Observations reveal tight correlations between black hole mass and various properties of the host galaxy, including the mass of the central bulge and the velocity dispersion of stars in the bulge. These correlations suggest that black holes and galaxies grow together, their evolution intertwined through feedback processes that regulate both star formation and black hole accretion. Sagittarius A fits these correlations reasonably well, suggesting that our galaxy's central black hole grew in concert with the Milky Way itself over billions of years. The black hole may have been smaller in the distant past, growing through the accretion of gas and the occasional merger with smaller black holes brought in by satellite galaxies. The current quiescent state may represent a mature phase in the black hole's life, with most of the available fuel already consumed or expelled from the central region. The future of Sagittarius A will be shaped by events both predictable and unpredictable. The collision between the Milky Way and Andromeda Galaxy, expected in 4 to 5 billion years, will eventually bring the supermassive black holes of both galaxies together. After the galaxies merge, their central black holes will spiral toward each other over millions of years, eventually coalescing in a violent merger that will release enormous energy in gravitational waves. The merged black hole will be significantly more massive than either progenitor, inheriting the combined mass of both objects. Before that distant merger, Sagittarius A will likely experience occasional episodes of enhanced activity as gas clouds or stars fall into its gravitational grasp. These feeding events will temporarily brighten the galactic centre, producing flares that may be visible across the electromagnetic spectrum. The frequency of such events depends on the supply of material in the central region and the orbital dynamics of stars and gas clouds near the black hole. We may be fortunate enough to witness such an event during our lifetimes, though predicting when one will occur remains beyond our current capabilities. The study of Sagittarius A haze provides a unique opportunity to understand supermassive black holes in detail. Its relative proximity, only 26,000 light-years away, allows observations with far greater resolution than possible for black holes in other galaxies. The Event Horizon Telescope has already produced images of the immediate vicinity of Sagittarius A haze, and future observations will reveal even finer details. Our galaxy's central black hole serves as a laboratory for testing theories of gravity, accretion physics, and the behaviour of matter under extreme conditions. The S stars, dancing around darkness. Among the most remarkable discoveries in galactic centre research is the existence of stars orbiting extraordinarily close to Sagittarius A. These objects, known collectively as the S stars, trace out elliptical paths around the supermassive black hole, some approaching within a few light hours of the event horizon. Their motions provide the most direct evidence for the existence of the black hole and allow precise measurements of its mass. Watching these stars dance around darkness has become one of the most productive endeavours in modern astronomy. The S stars were discovered through painstaking observations in the infrared, wavelengths that can penetrate the dust obscuring the galactic centre from optical telescopes. Beginning in the early 1990s, 2 independent research groups began monitoring stars in the central arc seconde of the galaxy, tracking their positions year after year with ever-increasing precision. One group, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, used telescopes at the European Southern Observatory in Chile. The other, led by Andrea Ghez at the University of California, Los Angeles, used the Keck Observatory telescopes in Hawaii. Both groups employed adaptive optics, a technology that corrects for the blurring effects of Earth's atmosphere in real time. Without adaptive optics, atmospheric turbulence limits the resolution of ground-based telescopes to roughly 1 arc second, far too coarse to distinguish individual stars in the crowded central region. With adaptive optics, the same telescopes can achieve resolutions approaching the theoretical diffraction limit, revealing details 10 to 20 times finer. This technological advance made it possible to track the motions of individual stars orbiting Sagittarius A. The star designated S2 became the most important object for understanding the central black hole. S2 is a young, massive star, roughly 15 times the mass of our Sun and perhaps 10 million years old. It orbits Sagittarius A on a highly elliptical path, completing one orbit every 16 years. At its closest approach to the black hole, called periaps, S2 passes within about 17 light-hours of Sagittarius A, roughly 120 astronomical units, or 4 times the distance from Neptune to the Sun. At this point, the star is moving at nearly 3% of the speed of light, or approximately 8,000 kilometers per second. The first complete orbit of S2 was observed in 2002, providing the first definitive proof that the mass at the galactic center must be concentrated in an extremely small volume. The orbital parameters allowed astronomers to calculate the central mass with unprecedented precision, confirming the 4 million solar mass figure and constraining the size of the region containing this mass. No known object other than a black hole could contain so much mass in such a small space. A cluster of stellar remnants, for example, would be dynamically unstable and would either collapse to a black hole or disperse on short timescales. The observations of S2 continued through subsequent orbits, with each passage providing new opportunities to test physical theories. The closest approach in 2018 was particularly significant, as the star passed close enough to the black hole for relativistic effects to become measurable. General relativity predicts that light climbing out of a gravitational field will be redshifted, losing energy as it works against gravity. This gravitational redshift was detected in the light from S2 during its close approach, confirming Einstein's prediction in the strong gravitational field near a supermassive black hole. The 2018 periaps passage also allowed measurement of the relativistic precession of S2's orbit. In Newtonian gravity, a star orbiting a point mass would trace out a closed ellipse, returning to exactly the same position after each orbit. General relativity predicts that the orbit will precess, with the ellipse slowly rotating over time. This effect was famously observed in the orbit of Mercury around the Sun, where it amounts to 43 arcseconds per century. For S2 orbiting Sagittarius A, the precession is much larger, roughly 12 arcminutes per orbit, and was successfully measured by both research groups. The detection of gravitational redshift and orbital precession in the S2 observations represents a triumph of precision measurement and a confirmation of general relativity in a new regime. The gravitational field near Sagittarius A is far stronger than anywhere in the solar system, providing a more stringent test of Einstein's theory. So far, general relativity has passed all tests with flying colours, but astronomers continue to search for any deviations that might point toward new physics. Beyond S2, dozens of other S stars have been identified orbiting within the central arcsecond. These stars have a variety of orbital periods, eccentricities and inclinations, creating a complex dynamical system centered on the black hole. Some S stars have even shorter orbital periods than S2. The star S62, for example, completes one orbit in only 9.9 years and passes within about 16 astronomical units of Sagittarius A at closest approach, even closer than S2. At periaps, S62 reaches velocities exceeding 6% of the speed of light, making it one of the fastest known stars. The star S4711, discovered in 2020, has an orbital period of only 7.6 years, the shortest known for any star orbiting Sagittarius A. Another star, S42714, achieves the highest known velocity at periaps, reaching approximately 8% of the speed of light, or 24,000 kilometers per second. These extreme velocities and close approaches provide ever more stringent tests of gravitational physics and probe conditions increasingly close to the event horizon. The existence of the S-stars raises an interesting puzzle. How did they get there? These are young, massive stars, only a few million to a few tens of millions of years old. They could not have formed in their current locations because the tidal forces from the black hole would tear apart any molecular cloud attempting to collapse into stars. Yet they orbit so close to Sagittarius A that they must have arrived there through some dynamical process after forming elsewhere. Several mechanisms have been proposed to explain the presence of the S-stars. One possibility involves the disruption of binary star systems. If a binary star passes close to the black hole, tidal forces can separate the two stars, capturing one on a tight orbit, while ejecting the other at high velocity. These ejected stars, called hypervelocity stars, have been observed fleeing the galactic centre at speeds exceeding 1,000 kilometers per second. The captured companions would become S-stars, their orbits gradually evolving through gravitational interactions. Another possibility involves the inspiral of massive young stars from a disk of gas and stars that may have existed around the black hole in the recent past. Evidence for such a disk comes from the observation that many young stars in the central parsec appear to orbit in one or two preferred planes, suggesting they formed from a common structure. Stars in such a disk could lose angular momentum through gravitational interactions and migrate inward toward the black hole, eventually becoming S-stars. The S-stars are not merely useful for measuring the black hole mass and testing relativity. They also serve as probes of the environment near Sagittarius A. By studying how their orbits evolve over time, astronomers can search for the gravitational influence of other objects in the region, including possible intermediate mass black holes or a distributed population of stellar remnants. Any deviation from the expected orbital evolution could reveal the presence of unseen mass. Future observations of the S-stars will provide even more precise tests of physics near the black hole. As monitoring continues over decades, the accumulated data will allow measurement of higher-order relativistic effects, including the precession caused by the spin of the black hole itself. Sagittarius A is expected to be spinning, as most astrophysical black holes acquire angular momentum through accretion, and measuring this spin would provide new information about the black hole's history and the physics of its immediate environment. The work of tracking the S-stars earned Reinhard Genzel and Andrea Ghez the Nobel Prize in Physics in 2020, shared with Roger Penrose for his theoretical work on black holes. The prize recognised decades of painstaking observations that transformed our understanding of the galactic centre and provided the most compelling evidence for the existence of supermassive black holes. The S-stars, dancing their intricate orbits around darkness, have become one of the most important tools for understanding the extreme physics at the heart of our galaxy. The Event Horizon Telescope breakthrough. For decades, astronomers dreamed of actually seeing the shadow of a black hole, the dark silhouette created when a black hole blocks light from the glowing material behind it. The challenge was immense. Even a supermassive black hole appears tiny from Earth, its event horizon subtending an angle of only a few tens of microarcseconds on the sky. To resolve such a small angle would require a telescope with a diameter comparable to the Earth itself. In 2019, the Event Horizon Telescope collaboration announced that they had achieved this seemingly impossible goal, producing the first image of a black hole shadow. 3 years later, they released an image of Sagittarius A, bringing the heart of our own galaxy into view for the first time. The Event Horizon Telescope is not a single instrument, but rather a global network of radio telescopes linked together through a technique called very long baseline interferometry. By simultaneously observing the same source from telescopes scattered across the Earth, astronomers can synthesize the resolving power of a telescope as large as the distance between the most widely separated stations. The Event Horizon Telescope Array includes facilities in North America, South America, Europe, Africa, and Antarctica, creating a virtual telescope spanning nearly the entire diameter of our planet. The technique works by recording radio waves at each telescope, along with extremely precise timing information provided by atomic clocks. The recorded data are then shipped to central processing facilities where powerful computers correlate the signals from different telescopes. The correlation process extracts the interference patterns that encode information about the spatial structure of the source. From these patterns, images can be reconstructed using sophisticated algorithms developed over years of research. The Event Horizon Telescope observes at a wavelength of approximately 1.3 millimeters, corresponding to a frequency of 230 gigahertz. This wavelength was chosen for several reasons. The angular resolution of an interferometer improves with shorter wavelengths, favouring observations at high frequencies. Additionally, the emission from the hot gas near black holes is relatively bright at millimeter wavelengths. Perhaps most importantly, millimeter waves can penetrate the scattering screen of ionized gas that blurs longer wavelength radio observations of the galactic centre. The first observing campaign capable of imaging a black hole shadow took place in April 2017. Over several nights, 8 telescopes on 6 mountains and 4 continents pointed simultaneously at 2 targets: Sagittarius A at the centre of our galaxy, and M87 Hikes, the supermassive black hole at the centre of the giant elliptical galaxy Messier 87. The observations produced approximately 4 petabytes of data, so much that it was faster to physically ship the hard drives to the processing centres than to transfer the data over the internet. The image of M87A was released first in April 2019 because it proved easier to process. M87 is over 1,000 times more massive than Sagittarius A, approximately 6.5 billion solar masses, which means that features in its accretion flow change on correspondingly longer timescales. Sagittarius A, being smaller, varies on timescales of minutes, causing the image to change even during a single night of observation. This variability complicated the image reconstruction process significantly. The M87 image showed a bright ring of emission surrounding a dark central region, exactly as theoretical models had predicted. The ring corresponds to light from hot gas orbiting the black hole, gravitationally lensed into a bright photon ring by the extreme curvature of spacetime. The dark centre is the black hole shadow, the region from which no light can escape. The asymmetry of the ring, brighter on one side than the other, results from relativistic beaming as material orbits the black hole at significant fractions of the speed of light. The image of Sagittarius A followed in May 2022, after years of additional analysis to account for the source variability. The image shows a similar structure to M87A, a bright ring surrounding a dark central shadow. The ring diameter is approximately 50 microarcseconds, consistent with the predicted size for a black hole of 4 million solar masses at a distance of 26,000 light-years. The image represents the first direct visual evidence of the supermassive black hole at the centre of our own galaxy. Creating the Sagittarius A image required developing new techniques to handle the rapid variability. The team generated thousands of possible images consistent with the data and used machine learning algorithms to identify common features. The final image represents an average of the most likely reconstructions, capturing the persistent structure while averaging over the variable features. Despite the challenges, the result is remarkably consistent with theoretical predictions based on general relativity. The event horizon. Telescope images do not show the event horizon itself, which emits no light, but rather the shadow cast by the event horizon against the bright background of accreting material. The size of this shadow depends on the black hole mass and to a lesser extent on its spin. By measuring the shadow size and comparing it to the mass determined from stellar orbits, astronomers can test whether the object at the galactic center behaves as general relativity predicts a black hole should behave. So far, all tests are consistent with the predictions of general relativity. The shadow size matches expectations for a Schwarzschild, or slowly spinning Kerr black hole of 4 million solar masses. No deviations from Einstein's theory have been detected, though the current observations are not yet precise enough to rule out all alternative theories of gravity. Future observations with improved sensitivity and resolution will provide more stringent tests. The Event Horizon Telescope collaboration continues to improve the array and conduct new observations. Additional telescopes have joined the network, increasing sensitivity and improving image quality. Observations at shorter wavelengths are being developed, which will provide even finer resolution. Plans exist for eventually extending the array into space, placing radio telescopes in orbit to create baselines longer than Earth's diameter and achieving resolutions capable of imaging fine details in the accretion flow. The movies of Sagittarius A represent the next frontier. By observing over multiple nights and tracking how the image changes, astronomers hope to create time-lapse sequences showing material orbiting the black hole. The orbital period at the innermost stable circular orbit is only about 30 minutes for Sagittarius A, meaning that dramatic changes should occur on timescales accessible to observation. Watching gas spiral into a black hole in real time would provide unprecedented insights into accretion physics and strong field gravity. The Event Horizon Telescope achievement represents a triumph of international collaboration and technological innovation. Hundreds of scientists and engineers from dozens of institutions around the world contributed to the project. The observations required precise coordination across multiple continents, and the data analysis pushed the boundaries of computational capability. The resulting images have captured the public imagination and opened a new window onto the most extreme objects in the universe. For the galactic center specifically, the Event Horizon Telescope observations complement the stellar orbit studies in important ways. The stellar orbits probe the gravitational field from light hours to light years from the black hole, while the Event Horizon Telescope probes the immediate vicinity of the event horizon. Together, these observations span an enormous range of scales and provide a comprehensive picture of the supermassive black hole and its environment. Sagittarius A has become one of the best-studied black holes in the universe, a cosmic laboratory for testing fundamental physics, Fermi bubbles and galactic outflows. Rising above and below the disk of the Milky Way, extending for 50,000 light-years in each direction, are two enormous structures known as the Fermi bubbles. These gigantic lobes of high-energy emission, discovered in 2010, reveal that the galactic center has not always been as quiet as it appears today. Something in the recent cosmic past released enough energy to inflate these bubbles, driving material far out of the galactic plane and filling vast volumes with energetic particles. The Fermi bubbles stand as monuments to past violence at the heart of our galaxy. The discovery came from data collected by the Fermi Gamma Ray Space Telescope, a NASA mission launched in 2008 to survey the sky at gamma ray wavelengths. Gamma rays are the most energetic form of light, produced by the most violent processes in the universe. The Fermi telescope detected gamma-ray emission from all across the sky, including the expected glow from cosmic ray interactions in the galactic disk. But careful analysis revealed something unexpected. Two enormous bubble-shaped structures centered on the galactic center, extending perpendicular to the disk. The Fermi bubbles span an angle of approximately 50 degrees on the sky, corresponding to their 50,000 light-year extent at the distance of the galactic center. Their edges are remarkably sharp, suggesting that they are bounded by shock fronts, where the expanding bubble material meets the surrounding galactic halo. The gamma-ray emission is relatively uniform across the bubbles, indicating that energetic particles fill the entire volume rather than being concentrated in particular regions. The energy required to inflate the Fermi bubbles is staggering. Estimates suggest that somewhere between 100,000 and 1 million supernova explosions worth of energy was released in a relatively short period of cosmic time. This energy accelerated particles to extreme velocities and drove material outward from the galactic center at speeds of hundreds to thousands of kilometers per second. The bubbles are still expanding today, though at a rate too slow to detect directly. Two main hypotheses have been proposed to explain the origin of the Fermi bubbles. The first invokes a period of intense star formation in the galactic center region, during which numerous massive stars formed, lived briefly, and exploded as supernovae. The combined energy of thousands of supernovae, supplemented by the powerful winds from massive stars, could have driven material outward and inflated the bubbles over millions of years. This scenario is supported by evidence for past star formation activity in the central molecular zone. The second hypothesis attributes the bubbles to past activity from Sagittarius A itself. Although the black hole is quiet today, it may have experienced episodes of much more vigorous accretion in the past. If Sagittarius AI temporarily became an active galactic nucleus, accreting material at a much higher rate and producing powerful jets, the energy released could have inflated the Fermi bubbles. This scenario is supported by the bipolar symmetry of the bubbles, which resembles the jet-driven lobes seen in active galaxies. The two hypotheses are not mutually exclusive, and both processes may have contributed to the bubble formation. The galactic center likely experienced both enhanced star formation and black hole activity at various times in the past, and the Fermi bubbles may represent the cumulative effect of multiple energetic episodes. Determining the relative contributions of star formation and black hole activity remains an active area of research. The age of the Fermi bubbles can be estimated from their size and expansion velocity. If the bubbles are expanding at roughly 1,000 kilometers per second, they would have taken approximately 15 to 20 million years to reach their current extent. This timescale is consistent with the light echo evidence, suggesting that Sagittarius A was much more active a few hundred years ago, though the bubble inflation likely began much earlier. The bubbles may have been inflated by multiple episodes of activity over tens of millions of years. The Fermi bubbles are not the only large-scale structures associated with the galactic center. In 2020, the eRosetta X-ray telescope discovered even larger bubbles visible in X-ray emission, extending approximately 45,000 light-years above and below the galactic plane. These eRosetta bubbles appear to be related to the Fermi bubbles, possibly representing an older or more extended component of the same outflow. The X-ray emission comes from hot gas with temperatures of several million degrees, heated by shocks as the outflow expands into the galactic halo. The existence of the Fermi bubbles has important implications for understanding galaxy evolution. The energy and material expelled from the galactic center affects the surrounding environment, potentially regulating star formation and redistributing heavy elements throughout the galaxy. Similar outflows have been observed in other galaxies, and they appear to play a crucial role in the feedback processes that connect supermassive black holes to their host galaxies. The Fermi bubbles provide a nearby example of these processes that can be studied in detail. The bubbles also affect cosmic rays in the Milky Way. Cosmic rays are high-energy particles, mostly protons, that permeate the galaxy and constantly bombard Earth's atmosphere. The Fermi bubbles appear to be filled with cosmic rays accelerated to extremely high energies, and these particles may eventually escape the bubbles and contribute to the overall cosmic ray population. Understanding the cosmic ray content of the bubbles helps constrain their origin and evolution. Observations at other wavelengths have revealed additional features associated with the Fermi bubbles. Radio observations show polarized emission from the bubble edges, indicating the presence of magnetic fields aligned with the bubble surfaces. Ultraviolet observations of distant quasars shining through the bubbles reveal absorption from gas moving at high velocities, confirming the outflow interpretation. These multi-wavelength observations paint a picture of complex, magnetized structures filled with hot gas and energetic particles. The Fermi bubbles remind us that galaxies are not static objects, but rather dynamic systems that evolve over cosmic time. The quiet galactic center we observe today is merely a snapshot in a long history of activity and quiescence. The bubbles preserve a record of past energetic events, much like geological strata preserve records of past conditions on Earth. By studying the bubbles, we gain insight into the history of our galaxy and the processes that shaped it. The G-objects, mysterious clouds. Among the most puzzling phenomena observed near Sagittarius A are the G-objects, a class of sources that behave unlike anything else in the galactic center. These objects appear as compact sources in infrared observations, but they are stretched and distorted as they approach the black hole, suggesting that they are at least partially composed of gas that can be tidally deformed. Yet they survive close passages to Sagittarius A that would completely disrupt ordinary gas clouds. The G objects occupy a strange middle ground between stars and clouds, and their true nature remains a subject of active investigation. The first G object, designated G1, was identified in 2005 through infrared observations of the galactic center. It appeared as a dusty, red source moving on an orbit that would carry it close to Sagittarius A height. A second object, G2, was discovered in 2011 and attracted intense attention because its orbit would bring it even closer to the black hole, with closest approach predicted for 2014. Astronomers eagerly anticipated this encounter, hoping to witness the tidal disruption of a gas cloud by a supermassive black hole in real time. The close approach of G2 in 2014 was one of the most closely watched astronomical events of the decade. Telescopes around the world monitored the galactic center as G2 swung around Sagittarius A host at a distance of only about 100 astronomical units, or roughly 3,000 times the Schwarzschild radius. At this distance, tidal forces from the black hole should have stretched and disrupted an ordinary gas cloud, potentially producing a spectacular flare as material fell toward the event horizon. What actually happened was far more subtle. G2 was indeed stretched by tidal forces, elongating along its orbit as the front of the object accelerated ahead of the back. The object developed a long tail of material trailing behind the main concentration. However, G2 was not completely disrupted. A compact core survived the close passage and emerged on the other side of the orbit, still intact. The expected fireworks, the dramatic flare from infilling material, never materialized. The survival of G2 surprised many astronomers and prompted a re-evaluation of the object's nature. A pure gas cloud should have been completely disrupted by the tidal encounter. The fact that G2 retained a compact core suggested that something was holding it together, most likely the gravity of a central star. The current leading hypothesis is that G2 and the other G objects are the products of stellar mergers, binary stars that spiral together and coalesced, surrounded by expanding envelopes of gas and dust. When two stars in a close binary system merge, the process is violent and messy. Material is ejected during the merger, forming a cloud of gas and dust around the merged remnant. This cloud gradually expands and disperses over thousands of years, but during this time, the object would appear as a compact source surrounded by diffuse emission, exactly like the G objects. The central merged star provides the gravitational anchor that prevents tidal disruption, while the surrounding gas produces the observed infrared emission and responds to tidal forces during close passages. The merger hypothesis explains several puzzling features of the G objects. Their infrared colours suggest temperatures of several hundred Kelvin, consistent with dust heated by a central star. Their sizes, a few hundred astronomical units, match the expected dimensions of post-merger envelopes. Their orbits, which bring them close to Sagittarius A, could result from the gravitational perturbations that often accompany binary evolution in dense stellar environments. Since the discovery of G1 and G2, several additional G objects have been identified, bringing the total to at least 6. These objects have a variety of orbital properties, with periods ranging from roughly 170 to over 1,000 years. Some have already passed through closest approach to Sagittarius A, while others have not yet reached periaps. Continued monitoring will reveal how each object responds to the tidal forces near the black hole, and whether the merger hypothesis can explain all of them. The G objects provide unique probes of the environment near Sagittarius A. As they pass close to the black hole, they experience extreme tidal forces that stretch and deform them in observable ways. By modelling these deformations, astronomers can learn about the gravitational field near the black hole and test predictions of general relativity. The gas stripped from the G objects during close passages may eventually fall toward the black hole, potentially producing detectable emission. The fact that G2 did not produce a dramatic flare when it passed close to Sagittarius A was disappointing for those hoping to witness a feeding event, but it provided valuable information about the accretion process. The amount of material stripped from G2 was apparently too small or too diffuse to significantly enhance the accretion rate onto the black hole. This observation constrains models of how material flows towards Sagittarius A and why the black hole remains so underluminous. The G objects also raise questions about the stellar population near the galactic centre. If these objects are indeed merger products, their existence implies that stellar mergers occur relatively frequently in the dense environment near Sagittarius A. Binary stars in this region experience strong gravitational perturbations that can destabilize their orbits and drive them toward merger. The G objects may represent just the tip of the iceberg, with many more merger products existing in the central region at various stages of evolution. Future observations will continue to track the G objects and search for additional members of this class. Each close passage to Sagittarius A provides an opportunity to study tidal interactions in real time, and the accumulated data will eventually reveal the true nature of these enigmatic sources. Whether they are merger products, young stars with circumstellar disks, or something else entirely, the G objects have added a new dimension to our understanding of the galactic centre environment. The galactic centre across the spectrum. Our understanding of the galactic centre has been built through observations spanning the entire electromagnetic spectrum, from radio waves to gamma rays. Each wavelength range reveals different physical processes and different components of this complex region. The dust that blocks visible light becomes transparent at infrared and radio wavelengths, while X-rays and gamma rays reveal the highest energy phenomena. By combining observations across all these wavelengths, astronomers have constructed a comprehensive picture of the galactic centre that no single type of observation could provide alone. Radio observations, as we have discussed, provided the first glimpses through the dusty veil and remain essential for studying the galactic centre. Radio waves pass through dust unimpeded, allowing us to see structures that are completely hidden at visible wavelengths. The radio sky reveals Sagittarius A itself, along with the complex of supernova remnants, ionized gas regions, and non-thermal filaments that populate the central region. Radio interferometry achieves the highest angular resolution of any astronomical technique, enabling the Event Horizon Telescope observations that imaged the black hole shadow. Infrared observations have been equally transformative. Infrared light, with wavelengths longer than visible light but shorter than radio waves, can penetrate dust much more effectively than visible light. Near-infrared observations, at wavelengths of 1 to 5 micrometers, reveal individual stars in the galactic centre region, including the S stars orbiting Sagittarius A. In the near-infrared, the hot blue stars that dominate visible light images fade away, and cooler red giant stars come into view, while the interstellar dust becomes remarkably transparent. Mid-infrared observations at wavelengths of 5 to 30 micrometers trace warm dust heated by nearby stars. Far infrared observations at even longer wavelengths reveal the cold dust in molecular clouds, those dark nurseries where new stars slowly take shape. The development of adaptive optics revolutionized infrared observations of the galactic centre. By correcting for atmospheric turbulence in real time, adaptive optics systems allow ground-based telescopes to achieve resolutions approaching the theoretical diffraction limit. Without this technology, the blurring caused by Earth's atmosphere would smear out the images of individual stars, making it impossible to track the S-stars on their orbits around Sagittarius A. The Nobel Prize-winning observations of stellar orbits depended critically on adaptive optics, which transformed fuzzy blobs into sharp points of light, whose positions could be measured with exquisite precision. Space-based infrared observatories have complemented ground-based observations by escaping the atmosphere entirely. Earth's atmosphere absorbs much of the infrared spectrum, particularly at wavelengths where water vapour is opaque. Space telescopes avoid this limitation and can observe at wavelengths inaccessible from the ground. The Spitzer Space Telescope, which operated from 2003 to 2020, provided stunning infrared images of the galactic centre region, revealing the distribution of stars and dust across the central bulge. The Wide-Field Infrared Survey Explorer mapped the entire sky at infrared wavelengths, cataloguing millions of objects, including many in the galactic centre direction. The James Webb Space Telescope, launched in 2021, represents the most powerful infrared observatory ever built. Its 6.5-metre primary mirror and suite of infrared instruments allow it to observe the universe with unprecedented sensitivity and resolution. Webb has already turned its gaze toward the galactic centre, revealing details invisible to previous telescopes. The telescope's ability to study objects embedded in dusty regions makes it ideal for probing the star-forming clouds and stellar populations near Sagittarius A. Future Webb observations will continue to deepen our understanding of this complex region. X-ray observations reveal the hottest and most energetic phenomena in the galactic centre. Gas heated to millions of degrees emits X-rays, as do particles accelerated to extreme energies in magnetic fields and shock waves. The Chandra X-ray Observatory, launched in 1999, has provided the sharpest X-ray images of the galactic centre, revealing a complex landscape of point sources and diffuse emission. Chandra observations detected the X-ray flares from Sagittarius A and mapped the distribution of hot plasma throughout the central region. The X-ray view of the galactic centre reveals structures invisible at other wavelengths. Supernova remnants appear as expanding shells of hot gas, their shock waves still propagating outward thousands of years after the original explosions. Pulsar wind nebulae, powered by rapidly spinning neutron stars, glow with X-ray emission from particles accelerated in the intense magnetic fields. Binary systems containing neutron stars or black holes accreting material from companion stars produce bright X-ray emission as the infalling matter is heated to extreme temperatures. One of the most striking features in X-ray images of the galactic centre is the diffuse emission from hot plasma filling the region. This plasma, with temperatures reaching tens of millions of degrees, cannot be gravitationally bound to the galaxy and must be continuously replenished by energetic processes. Supernovae, stellar winds from massive stars, and possibly outbursts from Sagittarius A all contribute to heating and maintaining this hot gas. The plasma may be slowly flowing outward from the galactic centre, contributing to the Fermi bubbles and other large-scale structures. Gamma-ray observations probe the most extreme energies in the electromagnetic spectrum. Gamma rays are produced by the most violent processes in the universe, including the acceleration of particles to nearly the speed of light and the annihilation of matter and antimatter. The Fermi Gamma Ray Space Telescope has mapped the gamma-ray sky with unprecedented detail, revealing the Fermi bubbles and detecting emission from the galactic centre itself. The gamma-ray emission from the galactic centre region has multiple components. Cosmic rays interacting with interstellar gas produce gamma rays through various processes, including the decay of particles called pions created in high-energy collisions. Point sources, including pulsars and binary systems, contribute to additional gamma-ray emission. And there is a mysterious excess of gamma rays from the inner galaxy that has sparked considerable debate about its origin. This gamma-ray excess, concentrated toward the galactic centre, has properties that some researchers argue are consistent with the annihilation of dark matter particles. If dark matter consists of weakly interacting massive particles, as some theories predict, these particles could occasionally annihilate when they encounter each other, producing gamma rays. The high density of dark matter expected near the galactic centre would enhance the annihilation rate, potentially producing a detectable signal. However, other explanations for the excess exist, including a population of unresolved pulsars too faint to detect individually. The debate continues, with the galactic centre serving as a potential laboratory for dark matter physics. Submillimeter and millimeter wavelength observations bridge the gap between infrared and radio, revealing coal dust and molecular gas in the central molecular zone. The Atacama Large Millimeter Array, located in the high desert of Chile, has revolutionized observations at these wavelengths. ALMA's unprecedented sensitivity and resolution have revealed the detailed structure of molecular clouds near the galactic centre, traced the motions of gas in the circumnuclear disk, and contributed to the Event Horizon Telescope observations of Sagittarius A. The power of multi-wavelength astronomy lies in combining observations across the spectrum to build a complete picture. A supernova remnant might appear as a shell of hot gas in X-rays, a ring of warm dust in infrared, and a source of radio emission from accelerated particles. By observing at all these wavelengths, astronomers can determine the temperature, density, composition, and energy content of the remnant, understanding it far more completely than any single wavelength could reveal. The galactic center, with its complex mix of stars, gas, dust, and energetic phenomena, particularly benefits from this multi-wavelength approach. The combination of observations from ground-based and space-based telescopes, spanning radio through gamma-ray wavelengths, has transformed our understanding of the galactic center over the past few decades. Each new telescope and each new wavelength range has revealed previously hidden aspects of this remarkable region. The picture that emerges is of a dynamic, energetic environment shaped by the interplay of gravity, magnetic fields, radiation, and the central supermassive black hole. And yet mysteries remain, ensuring that the galactic center will continue to attract the attention of astronomers for generations to come. The violent history of our galactic heart. The galactic center we observe today is merely a snapshot in a long and turbulent history. Evidence from multiple sources indicates that Sagittarius A and its surroundings have experienced dramatic changes over cosmic time, with periods of intense activity punctuating longer intervals of relative quiescence. By piecing together clues from observations and simulations, astronomers have begun to reconstruct this violent history, revealing a past far more eventful than the present calm might suggest. The Fermi bubbles, those enormous structures extending 50,000 light-years above and below the galactic plane, provide perhaps the most dramatic evidence of past activity. As we discussed earlier, inflating these bubbles required an enormous release of energy, equivalent to hundreds of thousands of supernova explosions. Whether this energy came from a burst of star formation, an active phase of the central black hole, or some combination of both, the event must have been spectacular by any standard. The bubbles are estimated to be roughly 15 to 20 million years old, meaning that the activity that created them occurred when early human ancestors were just beginning to walk upright on the African savanna. X-ray observations have revealed more recent evidence of past activity. The molecular clouds in the galactic center region show fluorescent X-ray emission that appears to be the echo of a powerful flare from Sagittarius A hoaxite. When X-rays from the flare struck the molecular clouds, they excited iron atoms in the gas, causing them to emit characteristic X-ray photons. By observing how this fluorescent emission changes over time as the light echo propagates through different clouds, astronomers have determined that the flare occurred approximately 100 to 400 years ago, depending on the geometry assumed. The intensity of this historical flare was roughly 1,000,000 times greater than the current luminosity of Sagittarius A, indicating that the black hole was temporarily much more active than it is today. The flare may have been caused by the tidal disruption of a star or gas cloud that ventured too close to the black hole, or by a temporary increase in the accretion rate from the surrounding gas. Whatever the cause, the event demonstrates that Sagittarius A can awaken from its slumber on timescales short compared to human history. Evidence for even more ancient activity comes from the structure of the galactic center region itself. The distribution of stars in the central parsec suggests that the region has been shaped by past energetic events. The nuclear star cluster surrounding Sagittarius A shows evidence of multiple episodes of star formation, with distinct populations of different ages. Some of these star formation episodes may have been triggered by gas inflows driven by the galactic bar or by the merger of smaller stellar systems with the galactic center. The presence of young, massive stars very close to Sagittarius A poses an interesting puzzle related to the region's history. Stars like those in the S-star cluster and the young stellar disks could not have formed in their current locations because tidal forces from the black hole would have prevented the collapse of molecular clouds. These stars must have formed elsewhere and migrated inward, or formed from a disk of gas that accumulated around the black hole. Either scenario implies past conditions quite different from what we observe today. Simulations of galaxy evolution suggest that supermassive black holes like Sagittarius A grew through a combination of gas accretion and mergers with smaller black holes. When the Milky Way absorbed smaller satellite galaxies over cosmic time, any black holes in those satellites would have spiraled toward the galactic center through dynamical friction, eventually merging with Sagittarius A. These merger events would have released enormous energy in gravitational waves and may have temporarily enhanced the activity of the central black hole. The relationship between black hole activity and star formation in the galactic center is complex and bidirectional. Bursts of star formation produce massive stars that explode as supernovae, injecting energy into the surrounding gas and potentially driving material toward or away from the black hole. Conversely, activity from the black hole can heat and disperse gas, suppressing star formation, or compress gas through shocks, potentially triggering new star formation. This feedback loop has operated throughout the history of the galactic center, shaping the stellar populations and gas distribution we observe today. The chemical composition of stars in the galactic center preserves a record of past star formation and enrichment. Massive stars produce heavy elements through nuclear fusion and distribute these elements into the interstellar medium when they explode as supernovae. By measuring the abundances of various elements in galactic center stars, astronomers can infer the history of star formation and chemical enrichment in the region. The results suggest a complex history with multiple episodes of star formation and possible inflows of gas from the larger galaxy. Looking further back in time, the formation of the Milky Way itself shaped the initial conditions for the galactic center. The galaxy likely formed through the hierarchical assembly of smaller structures, with dark matter halos merging and gas flowing inward to form stars. The central black hole may have formed from the collapse of massive gas clouds in the early universe, or from the merger of smaller black holes that formed in the first generation of stars. The details of this early history remain uncertain, but the galactic center we observe today is the product of billions of years of evolution. The future history of the galactic center will include at least one dramatic event: the collision and merger with the Andromeda Galaxy, expected in approximately 4 to 5 billion years. When the two galaxies collide, their central black holes will eventually spiral together and merge, releasing enormous energy in gravitational waves. The merged galaxy will have a more massive central black hole and a different structure than either progenitor. Our distant descendants, if any exist, will witness a galactic center quite different from the one we study today. The violent history of the galactic center reminds us that the universe is not static, but constantly evolving. The quiet black hole we observe today has experienced periods of intense activity in the past and will likely do so again in the future. The stars, gas, and dust in the central region have been shaped by billions of years of dynamic processes, and they will continue to evolve for billions of years to come. By studying the galactic center, we glimpse not only a remarkable place, but also a window into the processes that shape galaxies throughout the universe. The galactic center and the search for life. As we contemplate the galactic center, a natural question arises: could life exist in this extreme environment? The region near Sagittarius A presents both challenges and opportunities for the emergence and survival of life, and considering these factors illuminates the broader question of where life might exist in the universe. The challenges are formidable. The galactic centre is bathed in intense radiation from multiple sources. Massive stars pour out ultraviolet light that would sterilize unprotected surfaces. Supernovae occur more frequently in the dense stellar environment, periodically flooding the region with deadly radiation. The central black hole, though currently quiet, occasionally produces X-ray flares that would be hazardous to nearby life. Cosmic ray intensities are elevated compared to the solar neighbourhood, increasing the radiation dose that any organisms would receive. The gravitational environment near the galactic centre is also hostile. Stars pass close to each other more frequently in the dense central region, and these encounters can destabilize planetary systems. A planet in a stable orbit around its star might be ejected into interstellar space by a passing star, or its orbit might be perturbed into a configuration incompatible with stable climate. The tidal forces from Sagittarius A itself become significant within a few light years of the black hole, potentially disrupting planetary systems that venture too close. The intense stellar density creates additional hazards. Collisions between stars, though rare, occur more frequently near the galactic centre than in the galactic disk. The debris from such collisions could bombard nearby planetary systems with high-velocity material. The frequent supernovae not only produce radiation, but also generate shock waves that propagate through the interstellar medium, potentially stripping atmospheres from planets or disrupting the gas disks from which planets form. Despite these challenges, the galactic centre is not necessarily a complete dead zone for life. The same high stellar density that creates hazards also means that habitable planets, if they exist, would be more numerous per unit volume than in the solar neighbourhood. The intense radiation environment might be mitigated by planetary magnetic fields, thick atmospheres, or subsurface habitats. Life on Earth has demonstrated remarkable resilience, thriving in environments once thought too extreme, from deep-sea hydrothermal vents to the interiors of nuclear reactors. The complex chemistry of the central molecular zone is intriguing from an astrobiological perspective. As we discussed earlier, astronomers have detected numerous complex organic molecules in the gas clouds near the galactic centre, including molecules related to amino acids. These detections demonstrate that the building blocks of life can form even in extreme environments. Whether these molecules could ever be incorporated into living systems in the galactic centre is unknown, but their presence suggests that prebiotic chemistry is not limited to quiet regions like the solar neighbourhood. The question of life in the galactic centre connects to broader debates about the galactic habitable zone. Some researchers have proposed that life is most likely to arise in a ring-shaped region of the galaxy, far enough from the centre to avoid the intense radiation and gravitational perturbations, but close enough to benefit from the heavy elements produced by previous generations of stars. The solar system, located roughly 26,000 light-years from the centre, falls within this proposed habitable zone. However, the concept of a galactic habitable zone remains controversial. Life might be more adaptable than we assume, capable of arising and persisting in environments we would consider hostile. The galactic centre, despite its challenges, might harbour forms of life quite different from anything on Earth, adapted to conditions we can barely imagine. Until we can actually search for life in the galactic centre, which is far beyond our current technological capabilities, the question will remain open. The search for life in the universe increasingly focuses on understanding the range of conditions under which life can exist. The galactic center, as an extreme environment, helps define the boundaries of habitability. By studying the radiation environment, the chemistry of the molecular clouds, and the dynamics of planetary systems in this region, we learn about the factors that promote or inhibit the emergence of life. Even if the galactic center proves to be lifeless, understanding why would advance our knowledge of astrobiology. The galactic center also features in speculative discussions about advanced civilizations. Some researchers have suggested that a sufficiently advanced civilization might choose to locate near a supermassive black hole to exploit its energy or to use its gravitational effects for various purposes. The black hole could serve as a gravitational lens for communication or observation, or its rotation could theoretically be tapped for energy through processes like the Penrose mechanism. These ideas remain highly speculative, but they illustrate how the galactic center captures the imagination when we contemplate the possibilities of intelligence in the universe. For now, the galactic center remains a place we study from afar, using telescopes that span the electromagnetic spectrum. The 26,000 light-years separating us from Sagittarius A is an unbridgeable gulf with current technology, and even communication at the speed of light would take 52,000 years for a round trip. The galactic center is simultaneously part of our cosmic home and utterly remote, a place we can observe in exquisite detail but never visit. This combination of intimacy and inaccessibility gives the galactic center a unique place in our exploration of the universe. Mysteries that remain. Despite decades of intensive study, the galactic center retains many mysteries that continue to challenge astronomers. Each answered question seems to generate new puzzles, and the more we learn about this remarkable region, the more we realize how much remains unknown. These mysteries drive ongoing research and ensure that the galactic center will remain a focus of astronomical attention for years to come. One of the most fundamental mysteries concerns the origin of Sagittarius A itself. How did a black hole of 4 million solar masses come to exist at the center of our galaxy? The standard picture involves the growth of a smaller seed black hole through accretion and mergers over billions of years, but the details remain unclear. Did the seed form from the collapse of a massive primordial gas cloud, from the remnant of an extremely massive first-generation star, or through some other process? How much of the current mass was acquired through gas accretion versus mergers with other black holes? These questions connect to broader issues in cosmology and galaxy formation that remain active areas of research. The spin of Sagittarius A is another unknown quantity with important implications. Black holes are characterized by only 3 properties: mass, spin, and electric charge. The mass of Sagittarius A high is well determined from stellar orbits, and the electric charge is expected to be negligible. But the spin, which describes how fast the black hole rotates, remains poorly constrained. The spin affects the structure of spacetime near the event horizon and influences the behavior of accreting material. Future observations, including more precise measurements of stellar orbits and improved event horizon telescope images, may eventually determine the spin of our galaxy's central black hole. The nature of the G objects continues to puzzle researchers. While the stellar merger hypothesis explains many of their properties, alternative explanations have not been definitively ruled out. Are all G objects the products of mergers, or do they represent a diverse population with multiple origins? How do they evolve over time, and what is their ultimate fate? Continued monitoring of known G objects and searches for additional members of this class will help answer these questions. The origin of the young stars near Sagittarius A remains incompletely understood. The S stars and the young stellar disks could not have formed in their current locations, so they must have arrived through some dynamical process. The details of this process, whether involving binary disruption, disk migration, or some other mechanism, are still debated. Understanding how these stars reach their current orbits would illuminate the dynamical history of the galactic center and the processes that shape stellar populations near supermassive black holes. The cause of the Fermi bubbles is another open question. While both starburst and black hole activity have been proposed as energy sources, the relative contributions of these processes remain uncertain. The age and formation history of the bubbles are also debated, with different models predicting different timescales and evolutionary sequences. Future observations at gamma-ray, X-ray and radio wavelengths will help constrain the properties of the bubbles and distinguish between formation scenarios. The gamma-ray excess from the inner galaxy, mentioned earlier, remains controversial. If this excess is due to dark matter annihilation, it would represent a major discovery with profound implications for particle physics and cosmology. However, astrophysical explanations involving unresolved pulsars or other sources cannot be ruled out with current data. Resolving this question will require either the detection of individual sources that can account for the excess or the identification of spectral or spatial features that definitively point to a dark matter origin. The magnetic field structure of the galactic center is complex and incompletely mapped. The non-thermal radio filaments suggest strong, organized magnetic fields in some regions, while other observations indicate more tangled field configurations. The origin of these magnetic fields and their role in the dynamics of the galactic center are not fully understood. Magnetic fields influence the behavior of charged particles, the propagation of cosmic rays, and the accretion of material onto the black hole. So understanding them is essential for a complete picture of the region. The feeding habits of Sagittarius A present ongoing puzzles. Why is the black hole so underluminous compared to its potential? What determines the accretion rate, and why does it vary over time? The X-ray flares and infrared variability indicate that the accretion process is not steady, but the physical mechanisms driving this variability are not fully understood. Theoretical models of radiatively inefficient accretion flows have been developed, but testing these models against observations remains challenging. The future evolution of the galactic center is also uncertain. Will Sagittarius A experience another major feeding event in the coming centuries or millennia? How will the stellar populations evolve as massive stars explode and new stars form? What will happen when the Milky Way eventually merges with Andromeda? These questions extend beyond what current observations can answer, but they motivate ongoing monitoring and theoretical work. The mysteries of the galactic center reflect the broader mysteries of the universe. Black holes, dark matter, the origin of cosmic structure, the conditions for life, all these fundamental questions intersect at the heart of our galaxy. By studying the galactic center, we address not only the specific puzzles of this particular region, but also the deep questions that drive astronomy and physics. The galactic center is a natural laboratory for extreme physics, a window into cosmic history, and a reminder of how much we have yet to learn. The future of galactic center research. The coming decades promise exciting advances in our understanding of the galactic center. New telescopes, both on the ground and in space, will provide unprecedented views of this remarkable region. Improved theoretical models and computational capabilities will allow more detailed simulations of the complex processes at work, and the continued dedication of researchers around the world will ensure that the galactic center remains at the forefront of astronomical discovery. The Event Horizon Telescope collaboration continues to improve its capabilities. Additional telescopes have joined the array, increasing sensitivity and improving the coverage of the virtual Earth-sized dish. Observations at higher frequencies are being developed, which will provide finer angular resolution and reveal smaller scale structures near the black hole. The goal of producing movies of material orbiting Sagittarius A is within reach, and such observations would provide unprecedented insights into the dynamics of accretion and the nature of spacetime near the event horizon. Plans exist for extending the Event Horizon Telescope into space. By placing radio telescopes in orbit, astronomers could create baselines longer than Earth's diameter, achieving even higher angular resolution. A space-based extension of the Event Horizon Telescope could resolve the photon ring around Sagittarius A, a feature predicted by general relativity that encodes information about the black hole's mass and spin. Such observations would provide the most stringent tests yet of Einstein's theory in the strong field regime. The extremely large telescope, currently under construction in Chile, will revolutionize ground-based infrared observations of the galactic center. With a primary mirror 39 meters in diameter, the extremely large telescope will collect far more light than current telescopes and achieve correspondingly higher sensitivity. Its adaptive optics system will provide sharper images than ever before, allowing astronomers to track fainter stars closer to Sagittarius A and to detect the subtle relativistic effects predicted by general relativity. The extremely large telescope will be particularly valuable for studying the S stars and searching for stars on even tighter orbits around the black hole. Stars closer to Sagittarius A experience stronger relativistic effects, providing more sensitive tests of gravity theories. The telescope may also detect the gravitational influence of the black hole's spin on stellar orbits, finally measuring this elusive property, and it will search for pulsars near the galactic center, which would provide complementary probes of the spacetime geometry. Space-based observatories will continue to contribute to galactic center research. Future X-ray telescopes with improved sensitivity and angular resolution will map the hot plasma and detect fainter X-ray sources in the crowded central region. Proposed missions like the Lynx X-ray Observatory would provide transformative capabilities for studying the high-energy phenomena near Sagittarius A2. Gamma-ray observatories with better angular resolution could resolve the sources contributing to the gamma-ray excess and potentially detect or rule out a dark matter signal. Gravitational wave astronomy opens entirely new possibilities for studying the galactic center. The Laser Interferometer Space Antenna, a planned space-based gravitational wave detector, will be sensitive to the gravitational waves produced by compact objects spiraling into supermassive black holes. If a stellar mass black hole or neutron star falls into Sagittarius A, LISA could detect the gravitational waves from this extreme mass ratio inspiral, providing a direct probe of the spacetime geometry near the event horizon. Such observations would complement electromagnetic observations and test general relativity in new ways. Pulsar timing arrays, which use the precise timing of millisecond pulsars to detect gravitational waves, are sensitive to different frequencies than LISA. These arrays could potentially detect gravitational waves from the eventual merger of the Milky Way and Andromeda supermassive black holes, though this event lies billions of years in the future. More immediately, pulsar timing might detect the gravitational wave background from supermassive black hole mergers throughout the universe, providing statistical information about black hole populations and galaxy evolution. The search for pulsars near the galactic center is a high priority for radio astronomers. Pulsars are rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. A pulsar in a tight orbit around Sagittarius A would be an extraordinary probe of the black hole's properties, allowing measurements of its mass, spin, and the space-time geometry with exquisite precision. Despite extensive searches, no pulsars have yet been found very close to the galactic centre, possibly because the dense plasma in the region scatters and absorbs the radio pulses. Future searches with more sensitive telescopes and at higher frequencies may succeed where previous efforts have not. Theoretical advances will accompany observational progress. Numerical simulations of black hole accretion, magnetohydrodynamics, and stellar dynamics continue to improve as computational power increases. These simulations allow researchers to model the complex processes at work in the galactic centre and to make predictions that can be tested against observations. Machine learning techniques are increasingly being applied to analyse the vast datasets produced by modern telescopes, potentially revealing patterns and correlations that human researchers might miss. The galactic centre will also benefit from advances in multi-messenger astronomy, the combination of electromagnetic observations with gravitational waves and potentially neutrinos. A major event at the galactic centre, such as the tidal disruption of a star by the black hole, might produce signals across multiple messengers. Coordinated observations could provide a more complete picture of such events than any single messenger could offer. The infrastructure for multi-messenger astronomy is still developing, but the galactic centre is a natural target for such coordinated campaigns. Public interest in the galactic centre remains high, fueled by stunning images and exciting discoveries. The Event Horizon telescope image of Sagittarius A captured worldwide attention and inspired countless people to learn more about black holes and the universe. This public engagement supports continued funding for astronomical research and inspires the next generation of scientists. The galactic centre, with its combination of extreme physics and visual appeal, is an ideal subject for science communication and education. The future of galactic centre research is bright, with new discoveries surely waiting to be made. The questions we ask today will be answered, and new questions we cannot yet imagine will arise. The heart of our galaxy, that mysterious region where a supermassive black hole lurks amid swirling stars and gas, will continue to fascinate and challenge us. And in seeking to understand this remarkable place, we deepen our understanding of the universe and our place within it. Our cosmic address. As we near the end of our journey to the galactic centre, let us pause to reflect on what we have learned and what it means for our understanding of our place in the universe. The galactic centre is not merely an astronomical curiosity, but a fundamental part of our cosmic address, the heart of the galaxy we call home. We live in the Milky Way, a barred spiral galaxy containing several hundred billion stars spread across a disk roughly 100,000 light-years in diameter. Our Sun is one of these stars, an ordinary yellow dwarf located approximately 26,000 light-years from the centre, embedded in one of the spiral arms that give our galaxy its characteristic shape. We orbit the galactic centre once every 230 million years, carried along by the gravitational pull of all the mass interior to our orbit, including the supermassive black hole at the very centre. The galactic centre is thus the gravitational anchor of our cosmic home. Every star in the Milky Way, every planet, every moon, every asteroid and comet orbits around this central point. The 4 million solar masses of Sagittarius A, though enormous by human standards, is only a tiny fraction of the galaxy's total mass, but it marks the precise centre around which everything else revolves. In a very real sense, the galactic centre defines the structure of our galaxy and our place within it. The light we receive from the galactic centre today left that region 26,000 years ago, during the last ice age on Earth. When those photons began their journey, woolly mammoths roamed the northern continents, and our ancestors were creating the cave paintings at Lascaux and Altamira. The galactic centre we observe is thus a window into the past, showing us conditions as they were long before recorded history. And the light leaving the galactic centre today will not reach any observers at our location until 26,000 years in the future, long after our civilization has transformed in ways we cannot predict. This vast separation in space and time gives the galactic centre a dreamlike quality. We can observe it in exquisite detail, tracking the orbits of individual stars and imaging the shadow of the black hole, yet we can never visit or interact with it in any meaningful way. The galactic centre is simultaneously part of our home galaxy and utterly remote, intimate, and inaccessible at once. This paradox captures something essential about our relationship with the universe. We are embedded within it, made of its matter and subject to its laws, yet most of it lies forever beyond our reach. The study of the galactic centre connects us to the largest questions in science. What is the nature of gravity, and does general relativity accurately describe the extreme conditions near a black hole? What is dark matter, and can we detect its presence through its effects on the galactic centre? How do galaxies form and evolve, and what role do supermassive black holes play in this process? How common is life in the universe, and could it exist even in extreme environments like the galactic centre? These questions drive research not only on the galactic centre, but across all of astronomy and physics. The galactic centre also connects us to the human tradition of looking up at the night sky and wondering. The Aboriginal Australians who saw the celestial emu, the Maya who associated the dark rift with the underworld, the Greeks who imagined the milk of Hera sprayed across the heavens, all were responding to the same luminous band that modern telescopes reveal as a galaxy of hundreds of billions of stars. Our scientific understanding has transformed how we interpret what we see, but the fundamental impulse to observe, to wonder, and to seek understanding remains unchanged across millennia and cultures. The galactic centre reminds us of our cosmic context. We are not separate from the universe, but part of it. Made of atoms forged in the hearts of stars, living on a planet orbiting a star in a galaxy with a supermassive black hole at its centre. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created by nuclear fusion in stars that lived and died before our sun was born. Some of those stars may have orbited close to the galactic centre, in the dense stellar environment where massive stars form and explode on short timescales. We are, in a very real sense, children of the galaxy, connected to its centre by the atoms that make up our bodies. As you drift towards sleep, perhaps you can imagine the journey we have taken together. From the ancient observers who first wondered at the bright band crossing the night sky, through the pioneers of radio astronomy who detected signals from beyond the solar system, to the modern researchers who have imaged the shadow of a supermassive black hole. The story of the galactic centre is a story of human curiosity and ingenuity. It is a story that continues today, with new telescopes and new techniques revealing ever more details about this remarkable region. The galactic centre will be there tomorrow and the day after, and for billions of years to come. The black hole will continue to anchor the galaxy, the stars will continue their orbits, and the gas and dust will continue their slow dance of collapse and dispersal. Long after our individual lives have ended, long after our civilization has transformed beyond recognition, the galactic centre will endure, a constant presence at the heart of our cosmic home. And so we come to the end of our journey to the centre of the Milky Way. We have travelled 26,000 light-years in our imagination, from the quiet suburbs of the galaxy where our sun resides to the bustling heart where a supermassive black hole holds court amid billions of stars. We have explored ancient myths and modern science, radio waves and gamma rays, stellar orbits and event horizons. We have contemplated mysteries solved and mysteries remaining, the violent past and the uncertain future. The galactic centre is a place of extremes, where gravity reaches its strongest, where stars orbit at thousands of kilometres per second, where temperatures range from near absolute zero in molecular clouds to billions of degrees in the plasma surrounding the black hole. Yet from our vantage point 26,000 light-years away, all this violence and intensity is reduced to a soft glow in the summer sky, a gentle brightening of the Milky Way in the direction of Sagittarius. The universe has a way of making the most extreme phenomena appear peaceful when viewed from sufficient distance. Perhaps there is comfort in this perspective. The supermassive black hole at the centre of our galaxy, for all its power and mystery, poses no threat to us here in the galactic suburbs. The intense radiation, the gravitational chaos, the occasional flares and outbursts, all occur so far away that they reach us only as faint signals to be detected by sensitive instruments. We can study the galactic centre, marvel at its wonders, and contemplate its mysteries, all from the safety of our quiet corner of the cosmos. The stars that wheel around Sagittarius A have been doing so for millions of years, and will continue for millions more. The gas clouds that drift through the central molecular zone follow their own slow rhythms, collapsing here, dispersing there, forming new stars in an endless cycle of creation. The black hole itself, patient and eternal, waits at the centre of it all, its gravity shaping the motions of everything around it. These processes unfold on timescales so vast that a human lifetime is less than an eye blink in comparison. There is something deeply restful about contemplating such immense scales of space and time. Our daily concerns, our worries and anxieties, our plans and ambitions all shrink to insignificance against the backdrop of a galaxy. This is not cause for despair, but for peace. We are part of something far larger than ourselves, a cosmic story that began billions of years before we were born and will continue billions of years after we are gone. Our brief moment of consciousness is a gift, an opportunity to witness and wonder at the universe that made us. The ancient peoples who looked up at the Milky Way and created stories to explain its beauty were participating in the same fundamental human activity that drives modern astronomy. They sought to understand their place in the cosmos, to find meaning in the patterns of light and darkness overhead. Their stories of celestial emus and divine milk, of rivers in the sky and roads walked by souls, were attempts to make sense of something vast and mysterious. Our scientific stories, with their black holes and accretion disks, their gravitational waves and relativistic effects, serve the same purpose in a different language. Both kinds of stories, the mythological and the scientific, point toward the same truth. We are connected to the cosmos in ways both physical and spiritual. The atoms in our bodies were forged in stars, some of which may have orbited near the galactic centre before exploding and scattering their enriched material across the galaxy. The light that enters our eyes when we gaze at the Milky Way has travelled for thousands of years to reach us, carrying information about distant places and ancient times. We are not separate from the universe, but woven into its fabric, participants in its ongoing story. As you lie here in the darkness, perhaps you can feel that connection. The same gravity that holds stars in orbit around Sagittarius A holds you gently against the Earth. The same electromagnetic force that produces the radio waves from the galactic centre holds the atoms of your body together. The same nuclear forces that power the stars power the sun that warms our planet and makes life possible. You are made of the same stuff as the galactic centre, subject to the same laws, part of the same cosmic whole. The night sky, when we take the time to look at it, offers a kind of peace that is hard to find elsewhere. The stars do not judge us or demand anything from us. They simply shine, as they have for billions of years, indifferent to our presence yet available for our contemplation. The Milky Way stretches across the heavens, a river of light connecting horizon to horizon, inviting us to wonder and dream. The galactic centre glows softly in Sagittarius, keeping its secrets while revealing just enough to tantalise our curiosity. In the quiet of the night, with the stars overhead and the earth solid beneath us, we can let go of the tensions of the day. The universe will continue its slow dance whether we worry or not. The black hole will continue to anchor the galaxy, the stars will continue their orbits, the gas clouds will continue their cycles of collapse and dispersal. We can rest in the knowledge that we are part of something vast and beautiful, something that does not depend on our efforts or our understanding. The galactic centre has been there for billions of years, long before any human looked up and wondered at the sky. It will be there for billions of years more, long after our species has evolved into something unrecognisable or vanished entirely. This permanence, this cosmic constancy, offers a kind of reassurance. Whatever happens in our individual lives, whatever happens to our civilization or our planet, the galaxy will endure. The centre will hold, and yet, in another sense, we are the galaxy becoming aware of itself. Through our telescopes and our theories, our observations and our imaginations, the universe has developed the capacity to contemplate its own nature. The atoms that were once scattered through interstellar space have assembled themselves into beings capable of wondering where they came from and where they are going. This is a remarkable development in the history of the cosmos, and we are privileged to be part of it. So as you drift towards sleep, carry with you the images we have explored together. The supermassive black hole, dark and patient at the centre of everything. The S-stars, dancing their intricate orbits around the invisible giant. The molecular clouds, cold and dense, nurturing the seeds of future stars. The Fermi bubbles, vast monuments to past violence, slowly expanding into the galactic halo. The Event Horizon Telescope image, humanity's first glimpse of the shadow, cast by our galaxy's central black hole. Carry with you also the sense of connection that comes from understanding our cosmic address. We live in the Milky Way, a spiral galaxy 100,000 light-years across, containing hundreds of billions of stars. Our sun orbits the galactic centre once every 230 million years, carrying us along on a journey we barely perceive. The galactic centre, 26,000 light-years away, anchors our cosmic home and defines the structure of the galaxy we inhabit. And carry with you the wonder that has driven humans to study the sky since the beginning of our species. The same curiosity that led ancient peoples to create stories about the Milky Way leads modern astronomers to build telescopes and develop theories. The same desire to understand our place in the cosmos motivates both the Aboriginal elder, pointing out the celestial emu, and the Nobel laureate tracking stellar orbits around a black hole. We are all part of the same tradition, the same long human project of seeking to know the universe. The night is quiet now, and the stars shine steadily overhead. The Milky Way arches across the sky, its billions of stars blending into a soft glow. Somewhere in the direction of Sagittarius, hidden behind clouds of dust, but revealed by radio waves and infrared light, the galactic centre continues its ancient rhythms. The black hole waits, the stars orbit, the gas swirls and flows. The universe goes on, vast and beautiful and mysterious. Let your thoughts drift like clouds across the sky. Let your breathing slow and deepen. Let the immensity of the cosmos hold you gently, reminding you that you're part of something far larger than yourself. The galactic centre will be there when you wake, as it has been for billions of years, as it will be for billions more. For now, rest in the knowledge that you have journeyed to the heart of the galaxy and returned safely home. The stars will keep their watch while you sleep. The galaxy will continue its slow rotation, carrying our solar system along on its endless orbit. The supermassive black hole will remain at the centre, anchoring everything in its gravitational embrace. And tomorrow, or the next clear night, you can look up at the sky and know that you understand a little more about what lies in that direction, in that brightest part of the Milky Way, at the centre of our cosmic home. Sleep well, fellow traveller. The universe is vast and full of wonders, and there will be more to explore when you wake. But for now, let the gentle light of distant stars guide you into peaceful dreams. Let the thought of the galactic centre, that remarkable place we have visited together, settle into your mind like a stone sinking into still water. Let the ripples spread outward, carrying you deeper into rest. The journey to the galactic centre is complete. The story has been told. Now it is time to sleep, cradled by the same gravity that holds the stars in their courses, warmed by the same nuclear fires that light the galaxy, made of the same atoms that have travelled through cosmic space for billions of years. You are home, here on Earth, in the Milky Way, in the universe that made you. Rest now and dream of stars.